All
All
right, so
right.
we're recording.
Oh, hold on, I'm not ready.
Oh, okay. All right. Good morning, gamers. Uh, this is the Big Cheese and Master Dorian Gray.
Hello.
We're gonna be teaching guys about physics now. All
DC
right.
Circuits, Chapter 19.
Yeah, that. Uh, Hold on. How do I share the screen? All right. Can y'all see my screen? You can see my epic Kratos wallpaper. Yeah. All right. Let's go. And my epic Kratos wallpaper for Google. Yeah, quite excellent.
Of course.
All right, let's go to the drive. Boom, DC circuits, chapter 19. All right. All right, so the first part from lessons, I think 1 and 2 are mine, and then I'll let Master Great take it away.
For 3 and 4.
Yeah, for 3 and 4. All right. So in chapter 19, we're going to be looking at circuits, diagrams of circuits, and whatnot. And one of the most important things is to identify different labels in the diagrams of circuits that we're going to see to make sure that we know what they mean and we know what they do. All right. So the first one is the wire. Okay. Right. This is where all the current flows through, right? You can't have a circuit without, I mean, you can, but like it's going to be a bad circuit without wires. All right. Then you have the switches. Switches open and close circuit. When the switch is open, as it's shown right here, no current can flow, right? So it's basically like a stop. But when the switch is closed, current does flow. All right. We have a resistor. It provides resistance to the current flow. These can come in multiple different forms. It can come like just a regular resistor or like light bulbs or something like that. All right, the battery can't have uh, a circuit without a battery, right? It provides the power, source of DC charge flow, you know what I'm saying? Ammeter measures the current. Ammeters are always made in put in series with the rest of with the resistance, I think, right? And voltmeters are put in parallel with what you're measuring the voltage of. All right, that is donezo. EMF and terminal voltage. Okay, EMF is a measure of the energy that causes current to flow through a circuit. It can also be defined as the potential difference in charge between 2 points in a circuit. Electromotive force is also known as voltage, and it is measured in volts. All right, so electromotive force, that's EMF, and you can just think of it as the voltage. All right, internal resistance is the opposition to the flow of current offered by the cells and batteries themselves in the generation of heat. Internal resistance is measured in ohms. And little note here, all resistance is measured in ohms. So internal resistance is a type of resistance. So that's why it is also measured in ohms. All right, and this was a little bit confusing to me at first. So I'm gonna get out the, hold on. Can I not annotate? I can. I'm gonna get out the annotation real quick and I'm gonna show you what I mean, right? So you have this box, right? This is a battery, okay? And then current, right? Be flowing out of the battery and in like a circuit type of thing, right? Don't forget to have your resistance, right? So what internal resistance means is that the energy that's being produced, I'm going to turn this to red, energy that's being produced inside here, all right, it's like chemical energy or whatever, being produced inside here, it has to pass through the different little energy cells, right? And these different energy cells also have their own resistance to them. So it's not gonna it's not gonna come out like completely, the energy produced isn't gonna come out exactly the same amount because there's some resistance that's using up some of that energy, okay? And that can manifest in like heat or something like that, which is why some batteries heat up, kind of thing. Yeah. All right. That's yeah. All right. Terminal voltage. The voltage output of a device is measured across its terminals. Terminal voltage is calculated by V, stands for terminal voltage. And that's the EMF, which is electromotive force, the total volts, minus IR. IR stands for the internal resistance. So this minus this equals the terminal voltage. Okay, in circuits, there are two different ways you can make them. You can make them in series and in parallel. A series circuit is a circuit in which resistors are arranged in a chain, so the current has only one path to take. The current is the same through each resistor. The total resistance of the current of the circuit is found by simply adding up the resistance values of the individual resistors. All right, and the equation is I equals V over R. All right, so the important thing is that, actually, let me show you what it, yeah, this is a series circuit, right? You can see how there's only one path for the current to take. All right, so the big difference between series and parallel circuit is series is only one path, parallel, there's multiple paths for the current to take. And because of this difference, the equations that you would use to solve for the currents, the voltage, and the resistance differ. Okay, so for a series circuit, all right, yeah, for a series circuit, to find the voltage, you would add up the voltages of each thing that's producing power. So if there were multiple of these batteries here, like say one over here, that's pointing in the same direction, then you would add that voltage to this voltage to get the total voltage for the entire system. Okay, and we get V equals IR from the equation I equals V over R, yeah, because we just like multiply by R on each side, you get V equals IR. And this little EQ out on the bottom means equivalent resistance, which is basically the sum of all resistances in the system. All right. To find equivalent resistance, you just add up the resistances R1 plus R2 plus R3. And since V equals I, R, the equivalent resistance, you can just substitute R1 plus R2 plus R3 into here. You get V equals I, parentheses, R1 plus R2 plus R3, algebra. All right. And now this is very important, ladies and gentlemen, or ladies and germs, right? In a series circuit, current stays the same, all right? Stays the same, does not change. Big fact. Okay, parallel circuits. Components connected in parallel are connected along multiple paths so that the current can split up. The same voltage is applied to each component. A circuit composed solely of components connected in series is known as series circuit. Likewise, one connected completely in parallel is known as a parallel circuit. Okay, this is a beautiful example of a parallel circuit. You can see the multiple paths of flow that the current can take. And kind of like I was saying before, with series circuits, current stays the same. In a parallel circuit, the current is the sum of the current of each individual loop. So you find the current in this loop, find the current for this, find the current for that, and that is the total current. So for this, V over R equivalent equals V over R1 plus V over R2 plus V over R3. Another equation for this is I equals V over R EQ. All right. So all these equations you can basically solve for yourself kind of if you know the rules, right? We had our initial equation, I equals V over R, which we're just playing around with here, right? If I equals V over R and in the original and in parallel circuits, the current is equals I1 plus I2 plus I3, then with the equivalent resistance, it would be this is I, this is I, this is I, but it's V over R1 plus V over R2 plus V over R3, kind of subbing in for that because I equals V over R, right? So it's all kind of the same thing, all right? And this is a breakdown of this, I equals V over R1, so we get that, where we get that, and where we get that. Okay, for resistance, for parallel circuits, trying to find a resistance, you do 1 over the resistance, right? So if there was just 2 loops for this, you would do 1 over the resistance of one loop, and then plus 1 over the resistance of the second loop. You would obviously find the common denominator, and then flip them to get the equivalent resistance. Flip them and then add them together, equivalent resistance. Okay, and that is that.
Right. Now we're on chapter 19-3, which is Kirchhoff's rules. These come in especially handy when you're faced with a complicated circuit with multiple batteries or multiple entrances and paths for the current to flow, which may at first be a bit overwhelming and complicated, but you can break it down into simpler parts using these rules. Now, the first one is the junction rule, which basically says the sum of all current leaving a junction must equal the sum of all currents leaving the junction. Emeka, if you go to the next slide. So this is a junction, basically, where one wire splits into 2, or if 2 split into 1, 2 combine into 1. As you see on the one on the left, the 7 amps splits into 5 amps and 2 amps. And we know, thanks to the conservation of energy, it must equal 7. And one with variables on the right is just saying I1, which is the initial wire, has to be equal to I2 plus I3. If we go back one slide, the loop rule says the sum of changes in potential around any closed loop of a circuit must be 0. So if we go next, it's basically saying the voltage leaving a battery must return to 0 as it comes back to the battery. So all of the voltage must be used up in resistors or light bulbs or anything in the path of the current that flows. If you look at the one on the left, the battery on the bottom takes a path, goes to the right, it goes up, it goes left, down, and then back into the battery. And the one on the top does right, down, left, and then back into the battery. So each battery must have a voltage of 0 returning to the battery, even though, it must have a 0, which means that you wouldn't have current from one battery flowing into another one or going all over the place. And next slide. 19.4 is much simpler. It's EMFs in series and parallel charging a battery. This boils down to is when 2 batteries are facing the same direction, which is if one has negative on the left, positive on the right, and one next to it also has negative on the left and positive on the right, the voltages of the 2 batteries are added together, and you can think of it as just one bigger battery. But when they're facing opposite directions, the currents are going to be opposing each other, and the bigger battery is going to win out, which means that the current or the voltage is going to be the voltage of the larger battery minus the voltage of the smaller battery. And you can also use this to charge batteries. If you have an empty battery and you force electrons into the negative terminal, you can increase the charge of the battery. This is what I was saying before. If you were to line up these batteries, if you were to just move one around, you would see that they're facing opposite directions, and thus you would E is the EMF. So EMF of 1 minus EMF of 2 is equal to, you can do R1 plus R2, move it to the left side, you have I times R1 plus R2, which is total resistance of the circuit times total current of the circuit, and you get that the total voltage or EMF of the circuit is equal to E1 minus E2. And I think we're done. I
All
hope
right.
our presentation has been satisfactory.
Yes, very satisfactory. Might even be excellent.
Hope everyone is doing well, and we will see you next video.
Yeah, to see our beautiful FRQ. You know what it is. All right. How do I pause this? Is this okay? Hold on a second, because I'm not going to edit any of this. That's a lot of work. Let's see. Here we go.